Welcome to this lecture. We have already seen the RF amplifier design for conjugate or maximum gain, specified gain, then low noise amplifier design, then broadband amplifier design. Now, we will see another very important part, because in any transmitter, finally before sending the signal RF signal to the free space, we have a power amplifier where we try to give as much power we can, as much is possible to give power. So, that is a power amplifier, and that power amplifier generally has a very high signal level, but our till now whatever amplifier design we have seen, there we assumed small signal model, but in power amplifier it is not small signal, it is quite large amplitude of signal. And that in power amplifiers many time we operate it at class C, etc. So, generally nonlinearity may come in power amplifiers. So, if nonlinearity comes, how do we go about in RF power amplifiers? So, we will have to see power amplifier design. Actually, amplifier design we have already seen, but in power amplifier there are certain characteristics which are not, we do not pay any attention to them in low small signal amplifiers, but in power amplifiers or large signal cases we need to pay attention to them, because if we do not put that or if we do not restrict ourselves to within those constraints, then what happens due to nonlinearity, we generate some other spurious frequencies, etc. Also we saturate the amplifier, so its gain, etc. that falls. So, it is essential to understand this power amplifier nonlinearities. So, that we will see in this first lecture. Actually, there will be the next 2-3 lectures will be on this. So, the first one is power amplifier design 1. First, we will discuss about the nonlinearity at large signal values. I already said that at the power amplifier, which is the final stage of before antenna, the final stage of any transmitter, wireless transmitter, there this due to large signal the nonlinearity may come. So, we let us see those nonlinearities. So, at small signal levels linearity we maintain, but due to interconnects, joints, etc., at large signal values nonlinearity appears. How to characterize nonlinearity of any amplifier? Now, you see that S parameters characterization for large signal is an absurdity. Why? Because S parameters for small signal do not depend on power level. There we have seen that any voltage, any current, any voltage reflected and incident, that ratio that we take. But for large signal, due to nonlinearity, S parameters also become level dependent. We have already seen they are frequency dependent, but now that time also we said that they are bias dependent. At large signal they are highly on signal dependent. So, if it becomes again signal dependent, then suppose I am writing that S11 is equal to V1 minus by V1 plus when I have the V2 plus is 0. So, now if this ratio is again a function of, this is a ratio, but if it is a function of let us say V1 plus, then it is very difficult to have these parameters, because for every level then I will have to define these. That is why for large signal people do not use S parameters to characterize power amplifiers or characterize any block which is using large signal levels. So, what we will do? We will see there are various figures of merit or parameters for characterizing nonlinearity. One of them is 1 dB gain compression point, another is called dynamic range, another is called spurious free dynamic range, another is called third order intercept point. So, these 4 are very important characteristic. That is why we will see that power amplifiers generally they are specified in terms of this, not in terms of our usual S parameters or other those gain and other values. Now, let us first see what is gain compression. We know that in a linear thing, if we plot the transfer characteristic, the power transfer characteristic of any 2 port network, particularly an amplifier. So, let us say that in the x axis we are putting input power in dBm, in our y axis we are putting output power in dBm. Now, in the linear zone it is slope of 1, we know we have a linear thing. So, as we are increasing the power in the input, output is following, but after certain point we see that it starts falling. Now, why it starts falling we will later explain, but all systems have this, that this it would have gone infinitely with this dotted line, but in all practical systems we see that this curve, instead of going like this linearly, it starts this. So, this is when it starts deviating from this normal, we can say that it is becoming nonlinear, for the transfer characteristic is no more nonlinear. Now, where I will say that it has become nonlinear, here or here or here or here or here. Obviously, when it is flat, I know that it is a nonlinear thing, it is saturated, but here where, so people have made this that we will not say that it is here, we will say that here it has become clearly nonlinear. This point is called 1 dB compression point. So, what is its definition? Now, it can be in terms of input power or output power, because this point, if I say this point has an x coordinate as well as this point has an y coordinate, that means this can be reference to input power level or output power level. Now, so that is why I am saying that input or output power point is 1 dB compression point. If it is input side, we call it input 1 dB gain compression point. If it is output side, we call it output 1 dB gain compression point. Now, what is the definition of this point? Because this point needs to be precisely defined to say that okay, I have already entered the nonlinear region, where this is the point where the gain has fallen 1 dB from linear small signal gain. You see, I was having some gain here, because this P out by P in was my power gain. Now, that would have been something in the linear case, but here you see I have got it. Please remember, this is a dB scale, that is why we are writing slope is 1. That does not mean that the gain is not there. In the dB scale, if I have a slope of 1, that means it is linear, but what it says that there is some gain. Now, linear gain is something, but here it is fallen by 1 dB from that, you see, that is why this is called gain has fallen 1 dB from linear small signal gain. So, in mathematical terms we can write that G at 1 dB gain compression point, that means here G in dB scale is 1 dB less than this point's power gain. So, this point power gain is the linear one. So, from that it has fallen to 1 dB. So, I know always this point that where it is, and I check that whether this is 1 dB, because had I checked it here, I would have seen that okay, still this difference between the linear thing and the actual thing, that is not 1 dB, but the moment it becomes 1 dB, this point we characterize that okay, in the actual graph this point represents the 1 dB compression point, this point also represents 1 dB compression point, this is the input 1 dB compression point, this is the output 1 dB compression point. Now, you can ask that why it is compression, it could have been that nonlinearity could have been, it gain could have been increased. Yes, it may increase also, but we will see that generally this is compression, not the expansion, but theoretically it is possible, and in some systems it may expand also. Generally we do not encounter such systems, but obviously with newer applications one day sometimes we may see expansion also. Okay. So, now if we see this, that means now I can say that from here to here I can use the system, because I want to have in amplifiers we need to have linear things. So, if the transfer characteristic is not linear, then amplifier will have problem. So, we need to define a range of input or output power levels where the amplifier will be behaving as linear. So, we say that this is the onset of nonlinearity. So, from this 1 dB gain compression point to the maximum minimum usable level, I will say range, that is called dynamic range of any amplifier or any two port network. Now, it is a very useful thing. It is the range of output power. Here I am saying in terms of output power, you can also dynamic range is also defined in terms of input power. So, range of output power where amplifier gain is linear. Now, upper range is fixed by gain compression. You see, the upper range is fixed by gain compression. We have not explicitly shown what is the lower range. Now, lower range is fixed by noise floor. If you, even if you do not give any input to any two port network, please look here that suppose I have a two port network and I am not giving any input here, but suppose output, this output I have no input here, but output I have connected to any oscilloscope or spectrum analyzer or something, a measuring device. So, there you will see always without signal also I have this. If I have a signal, then I get somewhere here, suppose I am looking at a spectrum analyzer, then you will see there is a signal, but in other places where no signals are there, still this. What is this? Because there are actually noises always present, particularly this particular block, it is adding some noise. Now, that is the noise floor of the device. In oscilloscopes, in multimeters, in spectrum analyzers, everywhere you have noise. In multimeter you do not have a visual display of that, but in oscilloscopes or spectrum analyzer you will see that there are noises. Now, that noise floor, so my signal should be sufficiently above that noise floor, actually several dB up from that noise floor. So, usable minimum usable range is always that noise floor plus some extra dB, so that I can recognize it as signal, because if my signal is such that instead of this, if the signal was also like this, I think you understand this red one, that instead of this, if I have signal like this, I will not be able to recognize it as a signal, even though it is a signal. So, minimum level of input signal should be sufficiently above noise floor. Typically, it is depending on what you prefer, that you may call this as signal, I may say no, unless and until it becomes like this green one I will not say. So, the green one is saying that his definition of signal is so much a bit higher dB than the red one's thing, but whatever you decide that okay, this is signal. So, that means there is above noise floor you have something. So, lower range of the dynamic range is fixed by noise floor. Now, let us see noise model of an amplifier. You see, I have a, I think the picture is not very visible. So, I have an amplifier. The amplifier has its gain, also it has some noise equivalent bandwidth. These terms I think you are familiar. Noise equivalent bandwidth, it is not the actual bandwidth, but that means a rectangular gain function that whatever bandwidth is give. Then it has some temperature and all equivalent temperature, noise equivalent temperature, and also it has the some noise figure. Now, when you have the input, obviously what we do, the source that will have some resistance, and we assume that source is a pure thing, it does not have resistance. Whatever source resistance we have, whatever noise it produces, because this will also produce noise, that we in abstract we say there is a temperature here, resistance here, whose temperature is at 290 degree Kelvin, and the noise, this whole signal part, source part that is producing, that is giving an Ni thing. Then the amplifier will be adding noise. Now, output of the amplifier is typically on a load, it is put. So, if I write that what is the to this amplifier, what is the input noise, let us call it Ni, and output noise is No. So, I can say that Pi, which is the input power to this amplifier, that will comprise of, one is the signal power, another is the noise power, because I will get in the input side both of these, and generally they are additive. So, Pi is Si plus Ni. Similarly, at the output I will get Po, which is So, which is the signal power, though actually always it is added. So, we cannot separately recognize it, but in mathematics we say that So is the signal powers level and No is the noise powers level. You know, this is a deterministic signal, this is a random signal. So, but when they are mixed we cannot separately say, but for analysis we do like this. Now, obviously you can now you can look at that what is the value of this output noise power. Output noise power is, since this amplifier has a gain G, so it will multiply this whatever this input noise power is coming, that means Gi G into Ni. So, that we are reckoning, and Ni we know that from this definition it is K Bn T naught, and also it will add its own power, that is its G into K Bn T, that whatever amplifier added noise, and this is amplified input noise. Oh, this thing should be amplifier added noise. So, the input noise it is multiplying with its gain, and its own noise that also is generated here, that also getting multiplied by its gain. Now, minimum detectable signal is what, because ultimately you will have to detect the signal. So, what is the minimum detectable signal? Now, this you know that noise figure and equivalent noise temperature, they are related by this. So, if you put this, the N naught becomes this, that we have already seen. Now, K T naught, K is a Boltzmann constant, T naught is the 290 degree, generally in European or in America or the advanced countries, they fix the standard as 17 degree centigrade, which is 290 Kelvin. So, this is a constant term. So, that turns out to be minus 174 dBm. So, we can write that output minimum detectable signal, that expression will be minus 174 dBm plus, you see from that this PO. So, it is SO plus NO. So, now minimum value is given by this, that PO MDS is minus 174 dBm plus 10 log Bn plus F is the noise figure plus GA plus X. This is the SNR margin I was talking above the noise floor. What is this? So, this is the minimum detectable signal, or this is the of the output side. So, it is always given by this. So, knowing the your amplifiers noise equivalent bandwidth, knowing its noise figure, knowing its gain, and knowing that SNR margin you fixed, typically if it nothing fixed, you take it either 3 or 4 dB above the noise floor. So, you can find the PO MDS. Once you have that, then you can define the dynamic range. You see, dynamic range is now analytically what is it? Previously we have seen it graphically, now we say that it is P output. This is the output dynamic range. P output from 1 dB gain compression point minus PO MDS. We know how to calculate MDS, we know how to, we have seen in graph this, later we will find out how to find this point, then you can always find the dynamic range. What is the physical significance of dynamic range? That means within this zone, if my output power level goes, depending on what gain I have, so I can have the corresponding input power level also, input dynamic range. So, within that level, if we keep my system, if I keep my amplifier, it will be linear. So, all whatever we discussed before of designing a small signal based amplifier concept, that design concept you can put. So, you need to know that in the power amplifier I will have this much dynamic range. So, I can vary my input power level or output power level, same thing. So, that within this range if I do, I am linear. So, all my amplifier design concept is valid. So, this is the definition of the dynamic range. Okay. Now, you see that there are, if I have a single spot frequency, then that dynamic range concept is sufficient. But as I said that generally we have in baseband, suppose when I am talking this baseband, the voice baseband, that is from 20 hertz to 20 kilohertz. So, I have various frequency components present over a band. Also, if I have a video signal, I have typically 4 megahertz, but if I want to play it more bandwidth, but over that also I have various frequency components present. Now, let us see the transfer characteristic of any power amplifier device. So, output voltage V naught T, that I can express as a power series, because in general I will try to make it as linear, but when I have as I said you have various interconnect joints etc. So, they are all not linear components. So, they are, or that linear means in electronics we always say superposition principle. So, for them superposition principle is not valid, that means the additive property and the scaling property, those are not valid. So, there I can also have these components, that the square of the input, the cube of the input etc., with the proper coefficients. Now, usually these A2, A3, they are these components, these coefficients of the nonlinear components, they are small. So, in small signal values, you see if I have VIT small, then this value is not much, this value is further smaller. So, that is why we that time assume that it is always this, but at this high small large signal cases I will see that we cannot neglect all of these. So, A1 is called linear gain coefficient, because this if VOT is equal to A1 VIT, then this is a linear thing, that is why it is a linear gain coefficient. A tone will generate up to nth order harmonic. You see that if I have a tone and if the system is nonlinear, so this Vi square t, that will make the second harmonic come. Then if I have this Vi 3, that means if A 3 is significant, I will have the third harmonic also get generated, because you know that if Vi t is cos omega t, it will generate a cos square. Cos square means there is a cos 2 omega term present. Similarly, if this is present, I will have cos cube. Cos cube means I have cos 3 omega t. So, we say that if we have nonlinearity like this, let us say up to mth order, then a tone will generate up to, here we are saying nth order. So, if we have nonlinearity up to n, that means I have sizable thing up to Vi to the power n, then up to nth order harmonic will get generated. Now, whether harmonic content significant or not, that depends on obviously these coefficients A 2, A 3, etc. This is called the second nonlinearity component, this is called the third nonlinearity component. If they are significant, then we will have significant harmonics, otherwise not. So, to have that how much nonlinearity we have, let us consider a two tone test. What is a two tones test? Though we have many frequencies, let us assume that we have two frequencies, one is omega 1 angular frequencies, correspondingly f 1 and f 2. So, we have this, with this is their coefficients, that means in my input signal I have this capital A 1 is the coefficient for this omega 1 component, capital A 2 is omega 2 component. Also, later we will see that in two tone test we assume that omega 1 and omega 2 they are different, but they are not very much far apart. So, omega 1 and omega 2 they are nearby, but two distinct components. Now, assuming that nonlinear system, what will be my output? V output will be A 1 into Vi t. So, in place of Vi t I can write this plus A 2 Vi t square, since Vi is this I can write this, plus A 3 Vi cube, then if more. So, that is why dot dot dot. Now, let us see what happens here. So, if you now make the terms, that what is the DC term, what is the omega 1 term, there will be omega 2 term, then there will be 2 omega 1 term, there will be 3 omega 1 term, etc. And if you list them, please do it at your home, you have this, please have it. You will see that DC will have amplitude this. You see, in the input there was no DC component, our input was typically this. You see, there are no DC component, but with the nonlinearity etc., this DC has come, there is a DC. Then desired frequency component omega 1, omega 1's component is this, omega 2's component is this, second harmonic means 2 omega 1 is this, then third harmonic is this, etc. Also, not only harmonics, there will be some other term. You see, if I have this term, let me see it. Now, when I have this term present, you see this A1, A2, etc. Now, there will be, if I have this, then there will be some terms which will be also omega 1 plus omega 2 or omega 1 minus omega 2 or 2 omega 1 plus omega 2, 2 omega 1 minus omega 2, 2 omega 1 minus 3 omega 2, etc. That means, harmonics are those that omega 1. So, for omega 1 I have omega 2 2 omega 1, 3 omega 1, 4 omega 1, that means integral multiple or subharmonics half omega 1 or 1/3 omega 1 or 1/4 omega 1, etc. But when I have two tone, not only them, there will be mixture of omega 1 and omega 2. That means I can write that now this is not an harmonic. You see, this is harmonic of omega 1 mixed with another harmonic of omega 2. This is called IM or intermodulation product. So, let us see these intermodulation terms. Now, type, what is second order IM? Now, if this M, whatever may be this plus minus thing, but M plus N, if that M and N are integers, M plus N is, if it is 2, it is called second order IM. If M plus N is equal to 3, it is called third order IM. So, you see that when I have omega 1 plus omega 2, basically I have M is 1 and N is 1. So, 1 plus 1 2. This is also, even though it is cos omega 1 minus omega 2, but that actually this coefficient is 1, this is also 1. So, this is second order IM. Then third order IM, you see 2 omega 1 minus omega 2. So, 2 plus 1, that is why it is third order IM. Here you see 2 plus 1, that is why it is third order IM. Here you see 2 1, so 3 1 2, so 3. So, all these are third order IM. So, that means frequency component 2 omega 1 minus omega 2, 2 omega 2 minus omega 1, 2 omega 1 plus omega 2, omega 1 plus 2 omega 2, all these are examples of third order IM. Similarly, if I could have a 3 omega 1 minus 2 omega 1. Now, what is this? This is actually which IM it is? It will be fifth order IM. Sorry, this is omega 2, fifth order IM, because this is 3, this is 2. So, it is a fifth order intermodulation product. So, here we have listed what are the amplitudes. You can cross check, you do it yourself, all this comes that. So, amplitude will be, actually I have written cos to show you the frequency part. Amplitude will be simply A2, A1, A2, here 3, 4, this. So, you see this is interesting that this, let us see the harmonics. In harmonics, I have A1, etc., A3, etc. This is the desired component. In harmonics, you have A2 into this. In third harmonic, you have this. Then in intermodulation, you have this. And if you see the spectrum of intermodulation products, you see that my actual desired frequencies is this omega 1 as well as omega 2, because this is my actual band. Now, you see that DC is far away. Generally, this omega 1, omega 2 are RF frequencies. So, DC is far away. Omega 2 minus omega 1, that means this is the second order intermodulation, that is near this DC, because omega 1 and omega 2 are nearby. Similarly, 2 omega 1, it is double of that. So, it is far away from this zone. 2 omega 2, that is also far away. Omega 1 plus omega 2, far away. 3 omega 2, this is third order intermodulation. Here this third order intermodulation, this is third order intermodulation. But you see that along with my desired zone, this third order intermodulation product, some of the third order intermodulation product which are this bearing this minus sign, 2 omega 1 minus omega 2, 2 omega 2 minus omega 1, these two are nearby. Now, what is the problem with this? That typically what we do when we have this, finally we put a filter and filter out this portion. but this portion has also come nearby. So, when I try to filter, it is difficult to remove these two intermodulation products with this third order intermodulation products with this. You see second order intermodulation product is far away, so I can remove it. This third order intermodulation product, this third harmonic, they are further away. Fourth harmonic, fourth order intermodulation product, they will be further away, I can always filter that. But this third order intermodulation product given by 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1, they are in the same frequency band as my desired frequency band. So, by filtering I cannot remove them, that is the problem, that they will come and they will disturb my system, because these are not my desired frequencies. So, third order intermodulation, where from it came? Because of nonlinearity it came. If the system was linear, these were not generated. Now, nonlinearity also generated harmonics, but by filtering I can always remove them, but these I cannot remove. So, they will disturb me, that is where I will have to be more clear. When I have high small large signal level, I have nonlinearity present. In small signal also nonlinearity is present, but due to small signal level its value is much less compared to my desired signal. So, always even if it is present, it does not disturb, but at high values they are comparable with my desired frequencies, and by filtering I cannot remove the third order intermodulation. So, third order intermodulation is dangerous. I will have to characterize my system that third order intermodulation should not come, because if it comes it will disturb me. So, it is at low values of the input signal, it is not significant, but we will see at some point in high value it starts becoming significant, and I should not take my amplifier into that region or that level where it comes. So, this we have seen. So, summary of these nonlinear terms, this lecture will finish. So, we have seen the danger of third order intermodulation. We have seen that due to nonlinear terms, bias point of the active block gets changed. We did not have in the input any DC thing, but the DC thing has changed. So, the bias point of the active block also gets changed, this we should be aware. Gain compression, also I said expansion, though generally we do not see expansion at desired frequency, depends on A3 sign. This gain compression depends on A3 sign. Usually A3 is negative. A3 is the, remember A3 is the component by which we have characterized the nonlinear system. A3 into B I T cube. Now, that A3 typically is negative, that is why we get compression, and 1 dB gain compression is its figure of merit of this A3 thing. Creation of harmonics, we have seen that due to nonlinearity all the harmonics get created. Creation of intermodulation frequencies, linear combinations of the input frequency. We have seen second order IM, we have seen third order IM, and we have seen the danger of third order IM. So, in the next lectures we should quantify this third order IM, and then we will try to find out that how to characterize our system, so that this type of third order intermodulation products do not come. Thank you.